So next up, we need to talk about solving homogeneous equations. First is we got to talk about a homogeneous function, and then we need to talk about a homogeneous equation. And so just one note I want to make real quick. We're going to talk about this today with homogeneous equations. These are first order equations we're going to discuss. But later in the semester, we're going to talk about homogeneous again, but in a completely different way. And so the homogeneous now and the homogeneous later are going to be different things. It's not going to be a problem. It's not going to be confusing at all. So don't worry about it. I'm just sort of making that note now. I make a joke in class lots of times and I say, these equations that we're talking about today are homogeneous, and the one when we talk about homogeneous later on in the semester, we're going to call it homogeneous so we can tell the difference. Anyway, so homogeneous equation. A homogeneous function, I should say, is a function that exhibits a particular property. So if a function has the property that when we evaluate that function at tx, ty, we get t to the n times f of xy. So the idea is we're going to plug tx in every time we see an x. We'll plug ty in every time we see a y. And then what we'll be able to do is rewrite that function in this form here, such that it's t to a power times the original function itself. If the function has that particular property for some real number n, then the function is said to be a homogeneous function of degree n. And so it's pretty easy to do this. This is not complicated. This is something you could have discussed and may have discussed way back when you first learned about functions themselves. And so if we look at a here, f of xy equals x squared minus 3xy plus 5y squared. So this is a two-variable function. Both x and y are in this function. So I'm going to evaluate it at tx, ty. And so all I do is I plug tx in every time I see an x. So tx squared minus 3 times tx, and a ty in every time I see a y. So ty plus 5 times ty squared. And then I want to know whether or not I'll be able to write this as t to a power times this original function. So if you work with this, we're going to get t squared x squared minus 3t squared xy plus 5t squared y squared. Notice they all have a t squared in them, and so I could write this as t squared times x squared minus 3xy plus 5y squared, which just so happens to be t to the second times the original function. And so therefore, f of xy is a homogeneous function degree 2. Oops, that disappeared. Degree 2. Pretty simple. Look at b. Okay. We're going to evaluate tx, ty. So we would get the cube root of t squared x squared plus t squared y squared. We could factor out a t squared. So you have the cube root of t squared times x squared plus y squared. Since these are multiplied together, I can take the cube root of each one, giving me the cube root of t squared times the cube root of x squared plus y squared. And this is the same thing as writing t to the 2/3 times the square root of x squared plus y squared, which happens to be the original, cube root of x squared plus y squared, which happens to be the original function. So this is a homogeneous function degree 2/3. Remember, n just has to be a real number, so it can be fractional, totally fine. Okay, any real number will work here. So this is a homogeneous function. This one right here is homogeneous function degree 2/3. Right. Here are two more. What's going to happen is you're going to get good enough at recognizing homogeneous functions that you're not going to have to do what we're doing right now. You're going to see a pattern start to develop of why something becomes homogeneous and why maybe it's not. And you may have already started to see that already, hopefully. So let's look at this one. F of tx, ty would give me t cubed x cubed plus t cubed y cubed plus 1. Now the problem here is this is a t cubed, this is a t cubed. There's no t cubed here that I can factor out and write it as t cubed times f of xy. I can't do that, which tells me that this is not homogeneous. Okay? Which is possible. I mean, this is not homogeneous. Let's look at D. Okay? F of tx, ty would give me tx over 2ty plus 4. And what happened is these two t's can cancel, and I get x over 2y plus 4, which happens to be the original function. And the question is, well, is that homogeneous? Well, couldn't I write this as t to the 0 times the original function? Yeah, so remember, n just has to be a real number. 0 is a real number, so this would be homogeneous. This function right here is homogeneous degree 0, which is possible. And so what we start to look at is what makes certain functions homogeneous and what makes them not. Well, it really has to do with the degree of the individual terms of the function. This term is a degree 3 term, this term is a degree 3 term, this is just a constant, which is a degree 0 term. If all the terms don't have the same degree, then there's no way it's going to be a homogeneous function. We look at this one. This is technically a degree 0 term because the numerator and denominator are both first degree, but they cancel each other out, and the constant is also a degree 0 term, and therefore they're all the same degree, and that's why it worked out to be homogeneous. Here are 3 more examples we can run through real quick, then I'm going to talk about a certain property that we're going to need in using homogeneous to solve differential equations. So first off, let's look at this one. If you look at the degree of the term, so this term right here is a degree 4 term because x is to the first, y is to the third. You add the exponents together, degree 4. Over here, same deal, degree 4. Since both terms are degree 4 terms, if we did the tx, ty thing, we would find out that this one is degree 4 homogeneous. Okay, so this is a degree 4 homogeneous just because of that. And if you need to check it, find f of tx, ty. But I think we should be able to not have to go through all that. Look at the next one. Look at these two terms in this function. This one's degree 2, this one's degree 1. This isn't going to work out to be homogeneous because I'm not going to be able to pull out t to a power and just get x squared minus y. It's not going to happen. So that one's not homogeneous. Following one here, x squared, technically this is a squared degree 2 term, and this is a degree 2 term. Again, add the exponents together. You would get degree 2 here. So in this case, degree 2 homogeneous. I would like you to be good enough that you don't have to find f of tx, ty on these homogeneous functions. But when in doubt, do it. Right? If you're looking at one, you're going, I don't know if this is homogeneous or not. Well, then go ahead. Find f of tx, ty, and see what happens. Okay, so then we have this property here, which says that if I have a homogeneous function degree n, I know I'm working with a homogeneous function degree n. What I can do is I can take that function, I can rewrite it like this. I can pull out x to the n, and now I'm going to be looking at a function of 1 comma y over x, which basically means in the first register here, I would be placing a 1, and in the second register here, I'd be placing a y over x. Same thing here, I could also pull out a y to the n instead if I didn't want to pull out an x to the n, in which case I would get a function of x over y comma 1. I'll show you an example of that real quick here with, let's say, this one. Okay, this is degree 2, this is a degree 2 homogeneous. So what I can do here is I can pull out an x squared, in which case I would get x squared times 1 plus 3y over x plus y squared over x squared. And how do I get that? Because if I distribute this back in, I have to get this function, right? This is the same thing. This is still f of xy, right? It's still the same function, I'm just writing it in a different way. And again, since it was degree 2 homogeneous, I could pull out an x squared, degree 2. And so then I look at what is this really? Well, what that is really, that is f of 1 comma y over x. And think about it. This means I'm going to plug a 1 in here every time I see an x, and a y over x in here every time I see a y. First register, second register. And if I did that, you would see what would happen. If I plug a 1 in here and here for x, I would get 1 plus 3 times 1. Then if I plug a y over x in for the second register, which would be where y is up here, I would get y over x plus y over x squared, which, if you think about it, that is exactly what this is right here. So this is x squared times f of 1 comma y over x. I could have also pulled out a y squared, and I would have gotten this. It's a particular property that's going to be useful in our solving process. So something to note there. This is the important part about homogeneous functions when it comes to differential equations. So now you know what a homogeneous function is, you know some properties of homogeneous functions. Now it's important to talk about a homogeneous equation. So a differential equation of the form, let's get something a little lighter, m of xy dx plus n of xy dy equals 0 is homogeneous if both functions m and n are homogeneous functions, and here's the key part, of the same degree. So this equation is comprised of two functions, m times dx plus n times dy. And those two functions, m and n, have to be homogeneous functions of the same degree for the entire equation to be considered a homogeneous equation. Okay? Once you determine you have a homogeneous equation, which you should be able to determine just by looking at it, because we should be able to determine if we have a homogeneous function pretty easily just by looking at it. The next question is, well, then how do we solve it? And what we're going to do is we're going to use a substitution. There's two different substitutions we can use. We could either use y equals ux or x equals vy, where u and v are new dependent variables to help reduce the differential equation basically into a separable. One thing you're going to see throughout this unit is we learn a new method of solving a new type of equation by really turning it into something we've already studied and already learned how to solve. And so determining which one of these substitutions you should use is better discussed as we start looking at examples, because there's a reason why you might want to choose one as opposed to the other. And so what I'll do here is to show you how we're going to use this. I'm just going to pick the one of them, say y equals ux. So we're going to say, let's let y equal ux. Well, that means y is going to come out and ux is going to go in its place. So then that also means that dy has to come out and be replaced with something with u's and x's in it. Well, y is equal to a product. Okay, if you look at this, y here is equal to a product. And dy is the derivative of y. So in order to figure out what dy equals so I can pull it out, I would have to use the product rule. So the product rule for u times x would be u times the derivative of x plus x times the derivative of u. So u dx plus x du. So we have this substitution, which automatically gets us this substitution. So now, the dy, that's out. Okay? The y itself, here and here, that's out. And so we replace, with our substitution, we replace y with u times x, and dy with u dx plus x du. So now this is the new equation we're going to be looking at. But remember, m and n, these functions here and here, are homogeneous functions. Even after the substitution, they're homogeneous functions. So that means I can pull out an x to the n out of each one of these because they're the same degree. So let's say they're homogeneous of degree n, right? So I can pull out an x to the n out of the m function and be left with m of 1 comma u. Now, when we said it before in the previous slide I was working on, I said if you pull out x to the n, you'd be left with f of 1 comma y over x. So why do we have an x to the n and we're left with m of 1 comma u? Okay. Well, remember, y is u over x. So technically what we had here was m of u over x, and then we got rid of these two x's, and that's why we have m of 1 comma u. So we pull out an x to the n here, okay? We're left with m of 1 comma u, and the same thing happens with the n, because remember, they're the same degree. So I pull an x to the n out of each one of these, and I'm left with m of 1 comma u and n of 1 comma u. Okay, now what can I do? Well, what I can do here is in this equation, I can clear out that x to the n from this whole thing. Because what I'm going to do, in essence, is this. I'm going to factor out an x to the n because it's in both of them. And I'll have m of 1 comma u dx plus n of 1 comma u times the u dx plus x du equals 0. And what I really have here is a product. X to the n times all this. And it equals 0. So in the zero product property, what that tells me is either this equals 0 or all this equals 0. One of them has to equal 0. Well, I would tell you that knowing that this equals 0 does nothing for you, right? Knowing that x to the n equals 0 basically tells you that x equals 0. And in this case, if y equals u to the x, then that tells me y equals 0. Well, if y equals 0 is the solution to this differential equation, that doesn't really tell us a whole lot, because that's what we call the trivial solution. This equation is equal to 0. If y equals 0, yeah, of course this is going to equal 0. So that doesn't really do a whole lot for us, so we're going to ignore that. So that's where this drops off. This is what is more of a consequence for us. So then what we're going to do is we're going to look at what's left. Okay, let's get rid of some of this so we can see better. Well, what we're going to do is when we look at what's left here, what I'm going to do is I'm going to start distributing this out here. Okay, and when I distribute that out here, I'm going to have this piece here with the dx, and I'm going to group it together with this other dx and pull the dx out, and I'm going to get all this term here. And then this is what's going to be left over here. Okay? And so what happens here is this turns into a separable equation. I have all this which has u's in it. Right? If you look, all this right here, there are no x's. The only variable over there is u. And I'm going to divide that over and move it over with this other stuff that has u in it. And that's where I'm going to get this. What I'm also going to do is I'm going to take this x that's sitting here, and I'm going to divide that over here to the dx, and so I get dx over x. And if you look at what I have here is I have a separable equation. X and dx, and all this u's with the du. So then what am I going to do? Well, if it's separable, what I should do is I should integrate this one, I should integrate this one, and I got my solution. So this substitution will turn a homogeneous equation into a separable equation. And that separable equation will look like this, every single time. This piece will always be dx over x, and this piece will always be in this form. What you could do is think of this as a formula, and you could jump from the original differential equation down to here all at once. I don't like doing that. I don't think it's helpful. I think that makes things more complicated than it needs to be. You'll see as we move through a specific example how we get through this, and it's not as bad as maybe this looks right now. This is more the proof to show you that no matter what type of homogeneous equation we have, we'll be able to turn it into a separable. All right, so let's do a specific example. All right, let's go ahead and solve this differential equation. First off, we have to recognize that this is a homogeneous equation. Degree 2, therefore this is a degree 2 homogeneous function. Degree 2, therefore this is a homogeneous degree 2 function. Since both of these are homogeneous degree 2, the entire equation is homogeneous degree 2. Okay. That being said, now we got to decide what we're going to do. Well, first off, we got to make a substitution. I'm going to tell you, we're going to say, let's let y equal u times x. And you're not going to really know why we're choosing that particular one yet. I got to get through a couple of examples before it really starts to become clear, and I can explain better why we choose that substitution. So just bear with me here on that one. So y equals u times x, so then dy would be u dx plus x du. All right, so then next thing we're going to do is plug all that stuff in. So we're going to end up with x squared plus u squared x squared, because that's for y, times dx plus x squared minus x times ux. Then that's going to be times dy, which is u dx plus x du. And that should equal 0. So notice, x squared, I can factor an x squared out. It was a degree 2 homogeneous, and I'm pulling out an x squared. That's no coincidence. I'd be left with 1 plus u squared dx. Now look over here. I got an x squared, and these two together are x squared. I can pull that out. I'm left with 1 minus u times u dx plus x du. Okay. Now what we're going to do is we're going to clear out this x squared and clear out this x squared, because it's not really going to give us anything that's going to help. So next, what we're going to do is distribute this into here. So I'm going to have 1 plus u squared dx plus, if I distribute this into here, I'm going to have u minus u squared dx. I'm just multiplying the u here and here and then leaving the dx out of it. And then I do it here as well. So 1 minus u times x du. And I'm not going to bother multiplying any of that together. Okay. The reason is I'm going to say here's a dx, here's a dx. That means I'm going to put these together here. So if I put all that together, I'm going to have a 1 plus u squared plus u minus u squared. So the u squareds will end up canceling, and I'll end up with 1 plus u times dx. Plus, over here I still have 1 minus u x du equals 0. So now what I have here is it's time to separate. Put my u's with my du's and my x with my dx. So this will go over here. This x here will go over this way. And I end up with dx over x, which we said in the previous thing. That's one piece we're going to get. And the other piece is 1 minus u du over 1 plus u. So now it's time to say, well, it's separated. Integrate here, and I integrate the other side. That's just going to give me the c. That's where the c is going to pop up for this equation, for its parameter. This is a very easy integral to do. This would be log x plus this is the one that we're going to have to worry about doing. How hard this particular integral is to do really is how hard the entire problem is. This one will always be dx over x, so you're always going to get log x. This one's going to change depending on what m and n functions are, and this side's always going to be c. So this is the question mark. As long as we can do this integral, we're done. And so the question is, do you know how to do something like that? Well, there's a couple ways I can do this integration. I could do a substitution, try and get this to simplify a little bit more. I could do long division, and I could divide this and simplify it before I integrate. You know, lots of things we can work with here. I could try and split the fraction apart. But either way, you need to be able to do this integral. Once we get that integral, we're on our way. So we have this integral 1 minus u over 1 plus u du. And what I'm going to do is I'm going to make a substitution. I'm going to say, let's let 1 plus u equal t. Okay, I can't use u. You know, usually we do use substitution, but we already have u. I don't want to use x or y. We already have that. So let's just call t. So then dt would equal du. But I can also take this equation and write this as t minus 1 equals u. And so I'm going to change this integral into 1 minus u is going to be t minus 1, over t dt. In which case, we're going to get the integral of 1 minus t plus another 1, so that's going to turn this into 2 over t dt. And I think now you see this starting to work out pretty easily. I'm going to split this fraction apart, and I'm going to get 2 over t minus t over t, which would be 1 dt, giving me 2 ln of t minus t. Now we got to substitute in that t was 1 plus u, so that'll be 2 times ln of 1 plus u minus 1 plus u. Okay? So we have our solution, which, remember, when we did go back to our differential equation, we have ln of x plus, now we're going to have 2 ln of 1 plus u minus 1 plus u equals c. But thinking about it, this isn't done yet either. We made a substitution in the beginning that y equals ux. So that tells me that u equals y over x. And so my final answer shouldn't have u's in it, it should have x's and y's in it, because that's how my original differential equation was set up. Well, last step here is to now resubstitute this back in for u. But before I do that, I'm going to clean up this equation a little bit. I'm going to look at this so that I can possibly rewrite it in a better way. And what I'll do is I'll get rid of some of this logarithm stuff. So I'm going to bring this 2 in here. I'm going to move this over to the other side. So I'm going to have log x plus log of 1 plus u squared equals c plus 1 plus u. This whole thing right here is actually just one big constant, so I could replace that with just c at this point. Then I'm going to get rid of these logarithms and exponentiate both, well, put them together first, I should say. So I'm going to get the log of x times 1 plus u squared equals c plus u. Then exponentiate both sides, clearing out this logarithm. X equals 1 plus u squared equals e to the c plus u. Now this can be written as e to the c times e to the u. And here this is still just one big constant, so I'm going to replace that with c. Now, I think we're close enough to where we can now resubstitute. And so this looks a lot better than our last one, so I'm going to place y over x in here now. So x times 1 plus y over x squared equals c e to the y over x. And that looks a lot better than all this logarithm stuff. We could probably do one better. Here, this should have a common denominator of x. So I get x times x plus y over x squared equals c e to the y over x. And finally, if this is squared, each one of these is squared. Well, if this is an x squared and this is an x to the first, I can cancel those. And I would finally get x plus y squared over x equals c e to the y over x. To me, that's probably the best answer we can go with. I could also multiply this x over to the other side so there's no fractions, but now it's just a matter of all we're doing is moving things around. So we try and go as far as we can. We're not going to get this into an explicit solution. It's implicit, which is fine, but that definitely looks a lot better than this. But one thing we had to do was definitely resubstitute back into y and x and get rid of the u. Here's another one. So notice this function in front of dy, clearly degree 1. This term right here is degree 1. And this one may be questionable, but it also is degree 1 if you consider this being degree 2, but it's inside the square root, which makes the whole term degree 1. Again, if you're not sure, find f of tx, ty, where this whole thing is your f function, and you'll see it's degree 1. So anyway, this is a degree 1 homogeneous differential equation. I'm going to use the same substitution again, that y equals ux. So then dy equals u dx plus x du, in which case we're going to get 2 times the square root of ux squared plus ux dx minus x times u dx plus x du. And if my computer would stop acting up, we'd be able to do this a lot better. There we go. So we're going to be able to pull out an x to the first, because remember this was degree 1 homogeneous, so we're going to pull out an x to the first. We already have it here. What you're going to see here, here's an x to the first, and when I split this up, I'm going to have a square root of x squared, which will be an x to the first as well. So if I pull an x to the first out of that, I'm left with 2 times the square root of u, so u to the 1/2, plus u dx minus x times u dx plus x du equals 0. So now these two x's I can drop off for the same reason we've been doing it all along, and then this negative will distribute in here and here, and I can group this u dx with these other dx terms, and so I'm going to have 2u to the 1/2 plus u minus u, so they'll cancel, and then that'll be my dx, and then I'll have a minus x du equals 0. Now it's time to separate, in which case I'm going to get dx over x minus du over 2u to the 1/2. Well, now I'm going to integrate since it's separated here and here. Pretty easy integrals to do. This one will be log x. This one I have to bring the u up to the numerator, so it's u to the minus 1/2. So I'll have minus 1/2. Then the integral of u to the minus 1/2 would be u to the positive 1/2 times 2 equals, let's call that c. These will cancel. So then what I'm going to get is log x equals c plus u to the 1/2. We could leave it like that and then go back to resubstitute. Remember, u will end up equaling y over x, okay, because of our substitution here. Or I could also get rid of the logarithm. It's kind of personal preference. I think at this point we could just leave that logarithm there, in which case we're going to get log x equals c plus y over x to the 1/2. And that one was far easier than the last one, and mainly because this integral was really easy to do. And whatever happens in that integral is really going to be the indicator of how hard this whole process is. This integral, remember, is always going to be dx over x, or if we choose a different substitution, it'll be dy over y, but generally that's going to be an easy logarithm integral. And so here's our solution to the differential equation, again in implicit form, but not very hard to do. Here's another one, in which case we have degree 4 homogeneous. This is degree 4, this is degree 4, so degree 4 homogeneous. What I'm going to do here is I'm going to change up my substitution. I'm going to say I'm going to let x equal v times y. And therefore dx is going to equal v dy plus y dv. Now, why did I do this? Well, I changed my substitution for a reason. And this is where you're going to decide how to choose your substitution. When we choose a substitution for either x or y would be u times x, and then the dy is the u dx plus x du. This substitution is not really how I decide what I'm going to do. It's all about this substitution here. Because what happens is the dx or the dy is going to expand into this whole product rule piece, okay, here. And so I go back to my original differential equation. I go, okay, here's dx, here's dy. Whatever I do, one of those is going to expand and become much larger. And the function in front is going to have to distribute into that. Which one of these would be easier to distribute? Would it be easier to distribute this into an expanded dx, or distribute this x to the fourth, y to the fourth into an expanded dy? Well, to me, in this example, it's definitely easier to do the 2x cubed y into an expanded dx as opposed to the other. And so that told me I wanted to expand the dx over the dy. So if I'm going to expand the dx, then that tells me my substitution should have been the x equals vy substitution. Sometimes it doesn't matter. We've seen previous examples where it probably wouldn't have mattered either way. It wouldn't make your life any easier or harder either way. And ultimately, you can choose either substitution no matter what. I'm just trying to choose one that's going to make my life easier. And so I feel like expanding the dx in this example would be easier than expanding the dy. And so that's why I'm going to let x equal vy and then dx equal v dy plus y dv. So that's what you should look at in terms of which substitution you should choose. And so now I'm going to get 2 v cubed y cubed times y times dx, which is v dy plus y dv, plus x, which is v to the fourth, y to the fourth, plus y to the fourth times dy equals 0. The original one was degree 4 homogeneous, so I'm going to pull out now a y to the fourth. Since I changed my substitution, I'm now going to pull out a y to the fourth. Well, I have it there. Here I have a y to the fourth here and here. So I'm going to get 2v cubed times v dy plus y dv, plus this is going to be v to the fourth plus 1 dy equals 0. Again, I pulled it out and I canceled the y to the fourth already. So now what I'm going to do is I'm going to distribute this here and here, and I'm going to group my dy terms. I see a dy here and a dy here. So I'm going to get 2v to the fourth dy, plus I have this v to the fourth plus 1 dy, and they're going to have to come together. And then I'll have 2v cubed y dv equals 0. So these coming together will give me 3v to the fourth plus 1 dy plus 2v cubed y dv equals 0. Now I'll divide the y over here to group it with the dy, take the v's, put it here, and I end up with dy over y plus 2v cubed dv over 3v to the fourth plus 1 equals 0. And notice we get a dy over y. This was instead of having a dx over x. We're going to integrate that. And then we have a 2v cubed dv over 3v to the fourth. That's going to be the integral we're going to concern ourselves with for the most part. And then the integral of 0 will just give us c. So as long as we can do this integral, that's it. We're set to go. And you should see right away this is going to be a simple u substitution integral, u du to some extent. Okay? So we have dy over y plus 2v cubed dv over 3v to the fourth plus 1 equals, I'll just call this c. We know this is going to be a logarithm. This is, again, just going to be simple substitution where I can use u here because I haven't used u yet. U equals 3v to the fourth plus 1. du equals 12v cubed dv. So I don't have the 12, I have the 2. So if I divide by 6, I'll have a 2 here, which is what I have here. And this simply becomes log y. This one will then become the 1/6 du over u. So this is a plus. And this is c, so there's another logarithm. So I end up with log y plus 1/6 log u, but u was 3v to the fourth plus 1 equals c. And now it's just a matter of rewriting this thing into a form that looks best. There's the solution. It's in terms of v, so we got to get back to x. So remember, x equals vy, so that tells me that v equals x over y. But before I get there, I'm going to work with this. First off, I'm going to multiply everything through by 6, because I don't want to deal with the 1/6, because that could come into the log as a 1/6 power, which is really a 6 root, a little more complicated. But if I multiply everything by 6, I get 6 log y plus log of 3v to the fourth plus 1 equals 6 times c. I'm still going to call c. Then I bring this 6 in here as a 6th power. I'd rather do a 6th power than a 1/6 power. That's why I did this. And then I can bring these two logs together. So log y to the 6th times 3v to the fourth plus 1 equals c. Exponentiate both sides. That gets rid of this log here. This becomes e to the c, but e to the c is still just a constant. So this is now looking better. Y to the 6th times 3v to the fourth plus 1 equals c. I think now is a good time to resubstitute. So y to the 6th times 3 v to the fourth, so it'd be x to the fourth over y to the fourth plus 1 equals c. We could stop there. I think we're going to go one step further, and that's going to be make a common denominator of y to the fourth here. So y to the fourth, this will have a y to the fourth. So I end up with y to the 6th times 3x to the fourth plus y to the fourth all over y to the fourth equals c. Reason I did this is now I can cancel this, and I'm left with the y squared. So finally, y squared 3x to the fourth plus y to the fourth equals c. To me, that's probably the best answer we could give. That looks a lot better than anything we've had so far. I'd stop there. You want to distribute the y squared in there? Go for it. Not necessary. There you go. Again, implicit solution, fine, but this is the best form of that implicit solution. And we're just messing around with our algebra all the way through here to get it to something that looks a lot nicer. But it's definitely in terms of x and y at the end. That's really important. All right, we have this last one. This one needs some work. It doesn't look homogeneous right away because it's not in that form of m dx plus n dy equals 0. So we got to rearrange this a little bit, and then I think we can check to see if it's homogeneous. And if it's not, then it's got to be separable, and if it's not separable, then really we don't know how to solve it. Those are the only two equations we know how to solve so far. And so I'll move the dx over to the other side, and then I'll jump everything together so I get 0 equals y plus x e to the y over x dx minus x dy. So I'll look at it like that. So now I have my m and my n here, and it's a matter of what's the degree. Well, this is clearly degree 1. The question is this degree 1? Well, think about it. If I plug ty in there, I'd have a t. If I plug a ty in there, I'd have an extra t. And if I plug a ty and a tx in here and here, the t's would cancel. So therefore, I would be able to pull a t to the first out of this and just get the same function back again. So yeah, homogeneous degree 1. Pretty quick check. All right, so now the substitution. What are we going to do? Do we want to expand the dx or expand the dy? I clearly would rather expand the dy. There's very little going on with the function in front of that. So my substitution is going to be that y equals ux. So dy is u dx. Dy equals u dx plus x du. And don't forget, we also have this initial value problem. We'll deal with that at the end. And so we end up with 0 equals ux plus x e to the ux over x dx minus x times u dx plus x du. Now, x to the first, remember, degree 1 we said. This is degree 1. So we're going to pull out an x to the first. We got that here. We already have the x to the first pulled out here. So let's make this look a lot nicer. So u plus e to the x's cancel here, so e to the u dx minus u dx plus x du. So now this negative can distribute in here and here. I can group my dx's, and we can go to finish this off. So this will be u plus e to the u minus a u dx. So the u's cancel, just giving me e to the u du, or e to the x dx, e to the, tongue-tied, e to the u dx. And then this here is going to give me a minus x du. So divide this x here, divide this e to the u here, and I end up with 0 equals dx over x minus du over e to the u. Integrate, very easy in this case, because this will be e to the negative u when I bring it up. So I'm going to get c equals log x minus, or actually it should be plus, e to the negative u, because the integral of e to the negative u would cancel out with this negative here. Okay, not much to do here. I'll resubstitute again using this substitution that tells me that u equals y over x. So I get c equals log x plus e to the negative y over x. There's not really much to mess around here, turn it into a different form. That's it. Can't really do much else with it. So there's your solution. Now we got to solve the initial value problem, which is that y of 1 equals 1. So basically x and y are both 1. So we use that to solve for c. We get c equals log 1 plus e to the negative 1 over 1, which is really just e to the negative 1. Don't forget log of 1 equals 0. So this is basically telling me that c equals e to the negative 1. Well, if that's the case, then e to the negative 1, which is 1 over e, should be c. So c equals log x plus e to the negative y over x, and that will solve our initial value problem. So here's the solution to the diffie-q, here's the solution to the IVP. But we did this using homogeneous differential equations. Again, this one may be questionable for homogeneous more so than the rest, but you mess around with it a little bit, you can discern whether it's homogeneous fairly quickly. And if it's not, move on to the next thing. Right now, the next thing is separable, and that's all we have. So if it's not separable, it's not homogeneous. We don't have a method, which is then going to take us to the next thing. We're going to learn exact differential equations.